statistics. We're going to start off today talking about probability, but before we get to that, why study statistics? What do statistics do for us? Do they just exist to torment us? I might argue that if you ask people what their least favorite college course was, they probably will say statistics, but I'm here to tell you that statistics are useful and I think we can make it some fun. So we do need to use statistics, and I will hopefully convince you of that over the next few slides. So first of all, just to kind of start us off, we're going to talk about probability. Why do we need to understand probability? Partly it's because we need to know how likely certain events are. And actually, probability is kind of on your mind every time you step outside. You're taking on risk when you go out and do things. And what's the likelihood that I might be in a car accident today? Or what's the likelihood that I might come down with an illness, right? So it's important to understand our chances of things, the likelihoods of things. It's also helpful in terms of studying biology when we're looking at patterns across the landscape. Well, how probable are the patterns that we're seeing? Is this just kind of an off thing, or is it something that we might see all the time? And it's really important to understand how likely it is that the patterns that we see might be due to just chance alone, some kind of randomness in nature, or is it due to some underlying, factor that's driving a pattern? Okay, so nature is full of patterns, and the goal of most natural sciences are to find patterns in the noise of nature. Statistics is one of our best tools for doing that. How can we need to learn how we can best sample, how we can design our studies to increase our chances of seeing the patterns in nature through the fog of noise that exists out there. Once we've collected data, we need statistics to help us interpret the data, to show us what the patterns really are. And this is important because as humans, we're pattern seekers. We look for pattern everywhere. And statistics, what's really cool about it is it's a common language of pattern, and it can be applied to almost any area of study. So it will become helpful to you even if you don't stay in the sciences. So probability is related to uncertainty, and probability is everywhere. So, what's the chance it might rain today? That's a probability statement. How frequently does your community flood? Calculating the rates and frequencies of things like 100-year floods, that's part of hydrological measurements. And if you go down to the corner store and buy a lottery ticket, you might want to know what's your chance of winning. These are all probability statements. But there's uncertainty in the world too. So, there might be a chance of winning the lottery, but it's uncertain any day whether you might win or not. And that's because there's a lot of variation in the world. So I'm going to talk a little bit about probability in the context of pitcher plants. And pitcher plants are really cool because they extract nutrients from insects that fall into the pitcher and then drown, and then the plant digests them. Now, it's not a terribly efficient method of capture, and most insects escape. So you can calculate the probability of a successful insect capture. So here's some probability terms that will come in handy. First is event or trial. This is basically just something happens. So an insect visits a pitcher plant. The next term is called an outcome. Now the outcome of that event, the outcome of that visit, can result in two possibilities. Either the prey could be captured or the prey could escape. And if you want to do this as a scientist, you should sit there and watch many, many replicated events and see what the outcomes are. Okay, so those are called replicates. And you would visit the plant and you would record the outcome many, many times. And then a set of replicate observations would be your experiment, a set of trials that you would use to determine a pattern. So in terms of probability, we calculate the probability as the number of outcomes divided by the number of trials or the number of events. And so in this case, you'd have the number of prey captures divided by the total number of pitcher visits by insects. And if you get a p of 0.0, then you're pretty guaranteed that event never happens or would happen very, very rarely. A P of 1.0 would be that the event always happens. And a P of 0.5 would be an event that happens about half of the time on average. Now, we can't measure all of the pitcher plants in a population, but we can estimate these probabilities by taking samples from a population, by then summarizing the data from all of the samples using what's called a histogram, which I'll show you in a minute, where the y-axis, the vertical axis, is frequency of outcomes, and the x-axis is the outcome itself. And so, for example, you could go out every week and you could spend a day watching 1,000 insects, and you could tally the number of times the insect got captured or the insect escaped, and that would be your data set. And then for each week, you would determine the number of prey captured out of 1,000 and plot that on a histogram. And so this could be your histogram for several weeks of data. The number of prey that are captured out of 1,000 is shown on the x-axis or the horizontal axis, and then the frequency of times that that happened is shown on the y-axis, the number of observations. And these histograms tell us how frequently we see certain events based on a large sample. So based on this, what would be the most probable outcome? I'll give you a minute to think about it. So hopefully you thought of something around this, right? That this number, 7 insects captured out of 1,000, happened the most frequently, right? Although there's a lot of variation. Sometimes plants only caught, sometimes plants only caught 1, or sometimes they caught 9. But this would be the most probable outcome, the peak of the histogram. So we can't measure all the pitcher plants in a population. Instead, we can estimate the P, or the probability, by taking many samples from a population. And so here's another example of frequency. And in this case, you could see that the estimate might be somewhere over here, right? Somewhere around here. Okay. So sorry about that. That was my last slide. And I'll see you next time.